So here's a rigid body kinematics problem which uses the idea of no slip condition to find the angular velocity of that bar OA, or the lever as it's called. So here's what we have. We've got a circular disc, which is obviously this one here, and this is being pushed to the right, and it's being pushed with this speed, which is v in this particular moment in time. And then the disk, which is attached to the end of this shaft, is interacting with the lever. Okay, and as you might imagine, it's going to rotate the lever clockwise in this case because of the contact point between the disk and lever. Okay, so the disk rotates, the lever rotates. We just don't know how, but what we are given are the following things. So we know this velocity here, right? That's the velocity that that's the velocity of the shaft, which is acting to the right. And then we also have the radius of the disk, and we also have the distance from the center of the disk to the pivot where the lever is attached, right? And we know that distance as x. And what we have to show is that the angular velocity of the lever, not of the disk, of the lever, has this expression right here. So v over x and that square root. So let's think how we would do this. Obviously, we'll have to apply Euler's equation for velocity at some point. But before that, I think it's useful to try to understand what's happening with the disk and the lever. So obviously both of them are solid objects, and the lever is in contact with the disk. In other words, the lever arm is tangent to the disk's circumference, right? And because of that, we've got an angle of 90 degrees here. And that angle of 90 degrees means that we've got a right angled triangle, right? So we know two sides of that right angled triangle. So we know the radius, we know the distance x, which means that we can actually find this side, right? So x is the hypotenuse. So we can find this as being equal to square root of x squared minus r squared. Okay, so we know all the sides. So we can also find something about this angle theta. Okay, there's no angle that's being given to us, but we can find a few useful things such as sine of theta, right? So sine of theta is r over x, and we can also find cosine of theta, which is the square root of x squared minus r squared over x, right? So we're going to keep those in mind. We might have to use them a bit later, but until then, let's actually try to find what's happening at that sort of interface between the disk and the lever, right? So let's see what happens. What's the velocity of this point right here? So that's the velocity of the point which is sitting on the edge of the disk. Let's call this point P. And that point is in contact with the lever, okay? So let's try to find out how we can find the velocity of point P. So I'm going to draw the disk again, and let's say point P is going to be somewhere here, like this, and this angle here. So this angle we're going to use in a second. We call this angle theta, right? Which means that this angle here is going to be pi over 2 minus theta, right? So I'm going to write that as pi over 2 minus theta. And the center of the disk, let's call that C. And I'm going to put my coordinate system into point C like that. So this is going to be my positive x and my positive y direction. And this is what we have. We have the velocity of point P equals, according to Euler's equation, we've got the velocity of c plus a rotation above point C, which is omega cross ct. right? Everything is a vector. This is a vector product. So we're trying to find this. Let's talk about this first term right here, right here. So we know the velocity of the shaft is v, which means that the whole shaft moves as a whole because the shaft is a rigid body and it's moving to the right, which means that the center of the disk is moving with the same velocity as the shaft, right? So we actually know what VC is, and VC is V, that's the velocity that's given to us, multiplied by the unit vector I, okay? So let's rewrite this as follows. So we've got a VP equals to VI plus, and then we've got our determinant, IDK, and then omega is, this omega is not the omega that we're asked to find, right? This omega is actually the angular velocity of the disk, which let's call it omega zero, just to dispel any confusion. So this is 0, 0, and omega 0, which I don't know yet if it's positive or negative. I can sort of try to guess from how everything is moving, but I'll just make it positive by default. And then CP, that's the CP vector, which has two components, one along x and one along y. Okay, so we know the length of CP because that's the radius of the disk. And let's see what's the x component. So the x component of CP is going to be equal to this bit right here, which is radius times cosine of this angle. So it's the radius times the cosine of this angle, but the cosine of this angle is the sine of theta, right? Because of how trigonometry works. And then this height right here, this vertical component of CP is r cos theta, and we have 0. Okay, and that's pretty much it. So we've got the velocity of point P of this point on the edge is VI plus, and then let's see what the determinant gives us. So we've got I, and then we've got minus omega 0 r cos theta, and then plus J times, and then we have omega 0 r sine theta. Okay, so we're almost there. The only thing I'm going to do now is I'll just take this to the next page and I'll just put the terms together. So all the i's and all the j's so that it's a bit more clear. So VP is going to be equal to I times V minus omega 0 r cos theta, and then plus J times omega 0 r sine theta. And this is going to be called, let's say, Vx, and this is going to be called Vy. Okay, the x and the y components of the velocity of point P. So that's the velocity of point P. But we don't really know what omega 0 is, and we have to use this velocity somehow to find the angular velocity of the lever. Okay, so here's what's happening. The disk is actually pushing the lever. Okay, there's no doubt about it. And because the two of them are solid objects, as you might expect, here's what happens. So where point P is on the edge, here you've got the lever, which I'll draw a small section of. So as the disk moves, it's going to push the lever, and to be more specific, the, the component of velocity which is perpendicular to the lever, this is what gives the lever its own velocity. In other words, the velocity of the lever at this point is equal to this, right? Let's call this, let's see. So we've got A, B, C. Let's call this point D maybe. So the velocity at point D is equal to the velocity of point C in the normal direction. And those two actually have to be equal to each other if you think about it, because if the velocity of point P is greater than the velocity of the lever at point D, then it means the two would actually the two solid objects would merge, which is quite impossible. So this is the constraint we're looking for. Okay, so the velocity of point D, in other words, the driving force or the driving velocity of the lever's motion is due to the normal component of the velocity of P. Okay, so let's try to find out what this normal component is based on what we already know. So if I try to draw this again without the lever this time, so I'm just going to draw a point P right here. So point P has this velocity, which has a Vx and a Vy. So Vx is going to be in the x direction, and Vy is going to be in y direction, like this. Okay, and I'm looking at the velocity which is normal to the surface of the circle, of the disk, right? And if you use a bit of geometry, you'll figure out that this angle here is actually the same angle as theta, right? It's the same angle as this theta here. So this is what we're looking at. So this angle is the same as this angle, right? And we know the sine and the cosine of that angle, so we're good. So this VPN is given by those Vx and the Vy components. So that's going to be equal to Vy times cosine theta, right? Because Vy actually has a component along this normal direction, which is, let's call it Vyn, and then x also has a component along the normal direction, which is this one, which is Vyx, and the Vxn, and then the two of them added together give Vn or Vpn. Okay, so this is going to be plus Vx sine theta. And let's see what this is. So Vp in the normal direction is going to be equal to Vy. So Vy is what we found previously. So omega naught r sine theta. So omega naught r sine theta. And then don't forget the cos theta. Plus. And then we have Vx sine theta. So Vx is this thing right here. So it's V minus omega 0 r cos theta. Omega 0 r cos theta sine theta. And if you look at this, you'll actually notice, interestingly enough, that this term and this term will actually cancel out. And the result is just going to be V sine theta, which is nice and simple. So V sine theta is therefore the velocity of the lever at point D, which is sitting on the lever, right? So if I go here, I'll say that the velocity of D is going to be equal to V and then sine theta. But we know what sine theta is from the very first thing that we wrote here, which is sine theta is R over X. So that's V multiplied by R over X. And then if we look at the lever for a second, so we know the lever is attached, well, it's not really, it's hinged at point O, and this is point D, and the velocity of point D is equal to V R over X, right? Then we can actually find the angular velocity of the lever. So that is going to be as follows. So VR over X is going to be equal to omega. That's the omega of the lever this time, multiplied by this distance here, which we also know. And it's this side of the triangle, right? It's this side, which is square root of x squared minus r squared. So it's omega times square root of x squared minus r squared, which finally gives us that omega is equal to Vr over x, and then this is going to be multiplied by x squared minus r squared. And we can actually rearrange this slightly. So we can write it as omega equals, and then we can put the v and the x together, and then this we can move it into the square root underneath. So this will become 1 over square root of x over r squared minus 1. Okay, and if you look at this, and if you look at this, they're exactly the same thing. So we have shown that the angular velocity of the lever has this expression right here using Euler's equation for velocity. And that's it.